Welcome to Walk About the Galaxy, the live on tape astronomy podcast where the science is universal, the opinions are personal, and the hosts are legit. We are Strange, Charm, and Top the Astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney,
coming to you from the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Our website at www.walkaboutthegalaxy.com has been disinfected and is being updated as we speak, but
nice.
Maybe not as you listen. Check it out for the deets on our past episodes. What the kids say these days.
No.
They don't say deets.
No. They said it 10 years ago.
10 years ago? That's about where I am, though.
Yeah.
I'm learning always about 10 years behind. Check it out for details on our past episodes and see how to order a Walkabout shirt and support STEM education at the same time. Our stumper today is geological, which relates to one of our topics, earthquake or volcano.
Oh.
That's it.
That's it.
Earthquake or volcano. You can interpret that however you like.
I think volcano.
Why is that?
They seem pretty exciting.
You want to see one, or is that you feel safer, closer to a volcano?
No.
Okay.
Yeah, I don't know how to interpret this.
Well,
is
you
this
get to
a
choose
danger
your own
thing?
interpretation.
Is this an So I've been pretty close to volcano.
Yeah.
And it was not like
It
was active, but it was in Hawaii.
Yeah.
So it was active, but it was not like
Kilauea.
it was not explosively outgassing.
It was steaming and bubbling.
It was, we walked on like freshly solidified lava.
That's cool.
And it's super cool.
Yeah.
And they're fascinating. Just when they do explode, I mean, it's really scary and really dangerous, but it's super fascinating. And there's all sorts of cool physics that happens.
When I was a kid, a wee lad, we were in Sicily near Mount Etna, and you could see orange out of the top from a distance, and it had a pretty major eruption shortly after that. We were home, read about it.
Nice.
Yeah, I brought home a piece of lava from that, which is
nice.
Gone.
I did not bring home lava from Hawaii because that is bad to do from Hawaii.
Oh, really? They don't want you to do that?
No, the gods. It angers the
Oh,
gods.
I see. Okay.
Also, it's a national park, so you're not supposed to do that.
I see. Okay.
Right.
Jim?
James?
Well, I do think volcanoes are cool, but I'm terrified of them. So I'll pick earthquakes.
Have you ever been in an earthquake?
An earthquake would be scary, but I think I could enjoy it as long as I wasn't like in a big giant building or something. But like you could be outside on the street or in a field,
as long as you weren't right
and
on
I
the fault line.
I think this sounds like somebody who's never experienced an earthquake.
Has your
I have
brother
never
experienced
experienced
earthquakes?
Yeah, sure. He's lived in San Francisco for many years, so he's nothing giant, but you know, he's but it seems, but the thing I don't like about volcanoes is much like lightning. Like I'm terrified of lightning because you just never know.
Yeah.
Like.
Well, I think that's kind of the thing with earthquakes too.
It's true, but like
it's one of their signature features.
No, I know you can't predict when an earthquake's coming.
We're getting better.
Just meaning if I was hanging around and just palling around near Tenerife or something like that, near the big giant volcano there in the Canary Islands, I would just be.
You'd be constantly
anxious all the time because like it goes and then everybody dies.
Yeah, but I think we're better at predicting when the volcano is going to be like having a big event.
Most of the time.
I think we're not great at it, but we're better at it than for earthquakes.
Yeah, no, and I agree with you. Like rationally, I'm sure that way more people have died as a result of earthquakes than volcanic eruptions. I won't say I'm sure, but that strikes me as probably true. But still, I'm more afraid of volcanoes.
Yeah, I mean tsunamis are a result of earthquakes.
Oh, that definitely is. Yeah.
Yes. Anyway,
but volcanoes can cause climate change and all sorts of crazy things. So.
Which is one of the things
we'll maybe see about that.
Yeah, we'll be talking about volcanoes and climate change. Also, supernova and the importance of clocks. But first,
very explosive topics today.
Are clocks?
Yeah.
That seems like a strange thing to say after, and the importance of clocks.
I decided to go with it, even though
clocks kind
are
of killed
typically
it.
thought of as explosive, but you know.
Maybe if I had started with clocks and then done volcanoes and supernova, it would have worked better.
Clocks are pretty exciting.
Yeah. Usually not explosive, but that'd be
when
a fun
they're
gag
attached to a bomb.
Oh, there you go.
Yeah.
But first, this episode of Walkabout the Galaxy is brought to you by the reduced chi-square statistic.
Oh, jeez.
Oh, boy.
They say there are lies, damn lies, and statistics. We say there are descriptive statistics, inferential statistics, and if you've got the courage to find out whether or not all your fancy ideas hold any water, the reduced chi-squared statistic. Taking the chi-squared distribution and reducing it by the number of degrees of freedom can set you and your model free. Free from doubt that you don't know what you're talking about. To shore up your hypotheses, collect some data, and check them out with the reduced chi-squared statistic. Where's the beef?
That's a strange tagline for chi-squared.
Come on, give me a better one.
But it's a great tagline for Wendy's.
Ah, nice.
Thanks.
Nicely done. What's a better line for reduced chi-squared statistic?
I don't know, something about reduced something, or like, I don't know. I'll have to do some taglines.
Cutting prices, lowering prices, maybe.
Yeah.
Reduced. Yeah, maybe.
Oh yeah, isn't it Freedom Week here in Florida? There's like discounts on tickets and sporting goods and fishing gear.
I don't know about that because of the 4th of July. We're recording this at the eve of the 4th of July weekend. Yeah. There's some fun space news.
Lots of it.
And some that's sort of jealous making.
Yeah.
So coming up, we're recording this in July, shortly before 2 planned commercial suborbital launches with peoples on board.
I'm so nervous.
So previously, as our listeners know, Blue Origin announced that they would be doing their first flight of the New Shepard suborbital vehicle with people. So Jeff Bezos and his brother, Mark, I think, are going, and then they auctioned off a seat for the bargain price of $28 million plus a 6% fee.
Really?
Yes. You didn't know about the 6% plus the 6% fee.
I'm so glad I only bet $27 million.
Right. So the fee is like, the fee on this one auction bid for this 10-minute ride is like more money than I have got ever.
That's right.
Yeah. And then they announced the fourth and final person.
Have they said what the name of that person is?
They have not disclosed the auction winner publicly. It's not me, though, I'll let you know.
No. It'd be fun to have some guesses.
It was because of that 6%. It's like, forget about it.
I know, exactly.
That's a ripoff. The fourth person is, Jim, you'll appreciate this.
I know, I did. When I saw
excited?
this, I was so excited.
I was excited for a different reason.
Because this is, well, you tell me who it is, and I'll tell you why.
Her name is Wally Funk.
That's right.
And Wally is a nickname.
First of all, the entire name is amazing.
Yes.
But it's a woman named Wally. I've been yelled at before because I want to name every pet I've ever owned Wally.
Mm-hmm.
I just love the name Wally for some random reason.
All
my vehicles, my computer, its name is Wally. Like when the printer sees it, so everything is named Wally. But when I try and name my female cats Wally, I get yelled at for that because that's not a girl's name. But look,
there you go.
She's awesome,
and
her name is Wally.
Right.
Yeah.
So who is she?
So Wally Funk is one of the Mercury 13, which was this group of women who were privately trained in the same procedures and went through the same physiological and psychological testing that the Mercury 7 male astronauts went through with NASA. They were trained. They did all this at a place called the Loveless Clinic. There's some amazing books about the Mercury 13. And these women all actually many of them did better on some of the tests than the Mercury 7 astronauts did. They were all trained pilots and aviators, and they were amazing, but of course, because it was the 50s and 60s, they never got to fly.
Yeah, so she'll get to go into space.
Yeah. And now she's quite old now. She's 82 or something.
82, she'll be the oldest
person in space ever, yeah.
John Glenn was like 78 or something.
Yeah.
But if you've watched For All Mankind, which I've talked about a couple times on the show, it's a revisionist history, but in this revisionist history of the show, Molly Cobb is one of the main characters, and she was one of the Mercury 13.
Oh, nice. Yeah. So they're going July 20th, the anniversary of the Apollo moon landing.
Yes.
And just recently, more recently, Virgin Galactic announced that they're going to do...
Same day, I think, as the Wally Funk announcement.
Okay. They announced that their next flight, which will be on July 11th, that they will have a full crew. Now, their vehicle always has people in it because it's a piloted vehicle. It's a space plane in some sense. So every time it's flown, it's had at least 2 people in it. But this time it'll have 6 people. And
Yeah,
one of
I
those
was surprised.
people will be Richard Branson.
Oh,
Mhm.
that's so good.
But then one of them is somebody that we know quite
Yeah.
well. I've known her since she was an undergrad at
Yeah.
Purdue. Sarisha Bandla, who's now a VP for governmental relations or something like that with Virgin Galactic. She was the undergrad student at Purdue of one of our colleagues, Stephen Collicott, who does a lot of microgravity experiments. And you and I, Addie, have had interactions with her in various different settings over the years. And so we're super happy for her and also super angry that it's not us.
And I found out that she will be operating a research payload aboard the flight.
And a research payload
an
of
actual
our colleagues up the road
So it's our
at the University of
scientific
Florida.
research payload,
Yeah.
Go
So
Gators.
that's exciting, and they're in principle going July 11th. So there are the long-awaited suborbital space tourist
It's here.
trade may be really about to kick off this month.
Yeah.
So very interesting to see. I had a nerd news thing for you
I was going
guys.
to say there's been a couple of other spaceflight things. There's been bunches of launches. There was
Bunches and bunches.
200-something small satellites launched in the last week and a bunch of different flight providers.
Yeah.
There's a Virgin Orbit, SpaceX, and
Right.
one other, I think.
There was a OneWeb from
Oh, yeah,
Ariane.
from Ariane,
Yeah.
yeah. There was a Russian launch of OneWeb, I thought.
Oh,
I think that
maybe
was a
so.
Russian launch, yeah.
Okay. Yeah.
Anyway, lots of little satellites up. Great.
Yeah. I discovered accidentally, did you know that I wanted to have my space shuttle, Lego space shuttle here as a prop for our YouTube viewers. Well, I'm sure people are very excited to see a Lego. But
Who wouldn't
I
be?
sort of stumbled across this show. Did you know there's a show called Lego Masters?
Yeah, I do know. I tried it once.
Yeah.
Yeah.
It's very nerdy.
It's kind of nerdy.
It struck me as the kind of show that people who aren't nerds watch and go, bunch of nerds.
I've watched a couple of episodes. Shows like that drive me nuts sometimes.
Oh, why is that?
Because there's so much like overproduction and then fake, and it's just lying about the order of things happen and how long people are taking to do things.
Oh, right.
That it bothers
They
me
sort
a
of
little
fake it
bit.
out to like, they're
Yeah.
running out of time, and it turns out they had 3.5
Yeah,
hours.
like every
or
cooking
something.
show ever. Yeah.
Yeah, exactly.
Oh, yeah, yeah. Well, anyway.
But they make some really cool things
Yes.
on it.
I don't know. I found it
Did you
very
find
amusing.
it amusing?
Yes.
Okay. Do you like the host?
Will Arnett?
Yeah, he's entertaining, but
Yeah, I don't know. I liked him. I like him in certain
yeah.
contexts, like Arrested Development.
Yeah, of
Yeah.
course.
Okay, let's talk about time, because that'll be a good first topic, since my trivia has to do with time.
Okay.
Timekeeping.
Timekeeping. Yeah, this was just a small update. There's a so timekeeping is very important. A lot
It
of
is,
times.
and it's people.
Yeah.
People don't really appreciate
How important it is.
how important it is.
And people don't appreciate like how hard it is to keep accurate time and like how essential that is to everything we do these days,
Right.
right? So like the fact
Not
that
just these days, forever. Like, isn't that the
Sure.
only way you would know where you are on the ocean, right?
That's
When
right.
they
Yeah.
figured out how to keep accurate time, so you'd
That's
know
right.
your longitude while you're on the ocean.
and like
Exactly.
improvements in clocks and precision with timekeeping have been
Yeah.
essential as we continue to progress.
Yeah.
Mhm.
And like, go ahead.
Well, I was just going to give my favorite example, which is
Okay.
from
Deep Impact?
almost
Cassini.
Cassini.
Oh, yeah.
Yes. Where we made all these the data I work with is measurement centers, but it's true for all the observations. Any
Mhm.
astronomical observation, you have to know very precisely when you made that observation, because everything's moving around
Yeah.
all
Yeah.
over the place. And for the observations that I work with of Saturn's rings, they were made from a spacecraft orbiting Saturn, and so your telescope is moving. Of course, that's also true for telescopes on the Earth, because the Earth is moving,
Mm-hmm.
rotating and orbiting the sun and all that stuff, and that changes your interpretation of what you're looking at. And our measurements, the particular data I work with, it's a measurement every millisecond.
It's pretty fast.
And it actually matters. Was it this millisecond or the next millisecond
Yeah.
that we saw this particular brightness from the star? And then we have to track that back to, okay, where exactly in the universe was everything at that
Where
time?
in the universe was... Cassini mission.
All right, that's our next song.
This that was also just to expand on. That was also enormously important for the picture of the black hole, right? The Event Horizon Telescope,
Oh.
Yeah.
because they were doing interferometry, which basically meant they had to be looking at the same thing at the same time.
The wavefront of light.
That's right.
Just
you had to
blows my
know,
mind.
like, to some ridiculous fraction of a second, like
Yeah. Way
exactly
faster
when
than
you were
Less-
making these
less- much
Less than
smaller than a
millisecond.
much
millisecond.
smaller than a millisecond, and
Yeah.
it is insane.
Yeah.
How so clocks. Holy
Right.
crap.
And
Clocks,
so
man.
for those, they had the
Did
benefit
this
of
just
it.
blow your mind? It's explosively blowing your mind.
It is explosively
Oh,
blowing
there
my
you go.
mind.
Clocks.
Blows your mind.
Yes.
On Cassini, it had some kind of clock, but it wasn't a great clock.
Sure, because it was like
Drifted.
1980s technology.
And it's like, it's not a very fancy clock, and
Yeah.
so it's ticking along. It
Did it have a
ticked.
little AA battery? Just kidding.
I think it used plutonium,
Okay.
but whatever.
So did my clock at home,
It
so.
used
Yeah.
plutonium. But it ticked about 8 times per second, and then it would make these little markers in the telemetry that would come down, and then we would take a look at that on the Earth, we, the collective humanity,
Sure.
and try to figure out, okay, when exactly was that? And then there would be all these updates of files to help you interpret.
Yeah.
When the Cassini clock said it was 5 o'clock, what time was it really?
Yeah,
You know?
yeah.
And it's
Yeah.
complicated.
Oh,
There
yeah.
was recently the case of the Ingenuity a helicopter on Mars
Right.
where the time stamping got off on their images, and they were
Right.
using that time stamping to do their
navigation.
navigation,
Right.
and that's what caused the wobble, right?
Yeah.
So even at those scales, it can cause
Right.
really important
Yep.
changes.
And I assume to segue to what you're going to tell us, Addie, that for the Black Hole Telescope, Event Horizon Telescope, all those observatories are tied into atomic clocks, which
Right.
provide the highest level of
That's a good
accuracy.
Right.
That is a great segue. Yeah.
You're welcome.
Yeah. So we use atomic clocks a decent
I'm
amount here.
always looking out for you.
We use atomic clocks here on Earth, which are a little bit different than our typical
AA
digital
battery.
or AA battery analog clocks, which have beautiful mechanisms and all of that.
They
Yeah.
do.
But atomic clocks basically use an oscillator that is like stabilized on energy levels of atoms. So it's like
Right.
looking at that oscillation and using that. That's why it's called an atomic clock, because it's using atomic.
So it's using some natural frequency. So like quartz, that was a big sort of breakthrough in the commercial
Yeah.
clock landscape in the 60s or 70s or something, and then you could get like your Casio quartz technology,
Oh, yeah.
which used some sort of natural vibrational frequency of quartz crystal. The atomic clocks are looking at an energy transition time or something within like a cesium atom or something
Right,
like
yeah,
that.
one of the cesium-133, I think, the isotope of cesium, and it's just one particular transition, and you just it's you count so many of those oscillations, and we define that to be a second.
That's
Right.
that's
Yeah.
literally the definition of a second, right?
Yeah.
Is n
Right.
very, very, very
And it's
large
great,
number.
and it's great because, of course, this isotope follows, it's just fundamental laws of quantum mechanics, of physics, and so you can tell anybody else, this is my definition of a second, and they can reproduce a second
Right.
Mhm.
precisely.
So-
And atomic clocks are awesome because they're using the very thing we define time by to keep track of time. So
Right.
Yeah, so some folks at NASA and some other institutions have been developing what's called a trapped ion clock. So it's like sort of isolating the atom and the ions in the atom to make sure you're not having interactions with other things in the device, and using mercury ions. And working on doing this on the ground for atomic clocks on the ground, but also then to put in spacecraft. And as we were talking about, one of the really important things is keeping time on a spacecraft. A lot of times the way it does that is by like communicating back with Earth to set its time. But if you want to enable autonomous navigation, more deep space navigation, having a really stable clock on the spacecraft is really important. So there's been a test of this called the Deep Space, I don't know what's it called, the Deep Space Atomic Clock. That was hard.
very imaginative, very imaginative. Yeah.
You mean DSAC?
I do mean that, yes. Which is been on a
Just
spacecraft.
trying to get Jim to giggle.
There he
There
goes.
we go.
DSAC.
DSAC.
It's been on a spacecraft orbiting the
Just gonna
Earth
keep saying DSAC.
since 2019.
Okay.
And so there's just a new study reporting that they've set a new record for long-term atomic clock stability in space. more than 10 times the stability of current space-based atomic clocks, including those on GPS satellites.
Yeah, that's what surprised me, because I know the GPS is also another one of these examples where you really have to have that very high precision. And there are actual atomic, when I was a kid, atomic clocks were like this incredible new technology, and they were like the size of a house.
Right,
Yeah.
right.
You know, now they're just like on satellites, and the GPS satellites have them, but they're updated. They're like reset to terrestrial atomic clocks daily,
or multiple times a day. So some clocks have to be updated several times a day to maintain stability, and you want something like a nanosecond stability, because a nanosecond in orbit corresponds to somewhere around like a foot or a meter, depending on where it is in its orbit.
Right.
And like for GPS especially, you need to be able to maintain that stability,
Right.
and that's true for a spacecraft further out as well.
Right. So these are able to, this one is able to hold its accuracy for years.
Yeah, so this had a time
That's
deviation
amazing.
of less than 4 nanoseconds after more than 20 days of operation.
Okay.
And then they were doing this over a period of a number of years.
Okay. Cool.
And the other cool thing about this clock is that it's about ending its operational life on this spacecraft, but they're doing a follow-up. I think it's called Deep Space Atomic Clock 2.
DSAC 2.
Yep. Which is an improved version. And it's
Double
gonna be on the
DSAC.
No. That's not what it's called. Just called 2.
Now it is.
Only here. You heard it first on the walkabout.
Title of the episode.
It's going to be on the Veritas mission to Venus.
Right. Okay.
So this is one of the technology demonstrations they're putting on that,
Awesome.
that
Right.
science mission.
Yeah, having that ability enables the spacecraft to then its computer knows exactly where it is and where everything else is.
Yeah.
It's like if you know what time it is, and it's like, okay, I know where everything in the solar system is, so then I know when to fire my thrusters to put myself on the right new orbit or whatever, instead of having to have this long back and forth
I hate when I have to check my
conversation
watch
with
before I
JPL.
fire my thrusters. And it's
Speaking
not-
of
not
watches,
all-
how long till we get atomic clock watches?
Probably not very long if these are on little spacecraft.
I think it's going to be a long time.
I want one.
Yeah. But yeah, so instead of
Well,
having the spacecraft having to phone home to JPL or APL or whatever and say, okay, run your calculations or whatever, it can just do them all
on its own.
autonomously. That's
Awesome.
pretty cool.
Very cool.
Future.
Yeah. Well, that ties in to your trivia.
Crazy.
And Jim did not know the specifics of the trivia before, but hit on it exactly with
Oops.
the keeping of time on ancient ocean-going vessels.
Remember when we saw there was a bunch of cool clocks we saw when we went to Greenwich Observatory?
Exactly.
Oh.
It has to do precisely with one of those clocks.
Oh.
Yes. So in navigation, just as spacecraft need to know what time it is to know where everything is, to know if they're close to the planet or not, or where the planet is going to be when they get there. In ocean-faring vessels, you can figure out your north-south position by looking at stars.
Yes.
And
True.
measuring their highest latitude above the horizon tells you, or their highest altitude above the horizon can tell you your latitude. But because the stars rise and set, because the Earth is rotating, you can't tell where you are east and west unless you also know exactly what time it is.
Right.
And so that meant for long sea voyages, which in sailing vessel times took weeks or months,
Right.
you didn't know very well where you were east or west. And this had very, sometimes tragic consequences. There was a naval disaster in 1707 called the Scilly Naval Disaster, and I checked the pronunciation, hoping that it wasn't that. But Scilly are some islands off the southwest coast of England.
Okay.
And they're rocky. There's some rocks there, the islands, of course, and they're rocks that ships can crash into.
Right.
And in a storm in 1707, 4 British ships crashed and roughly 2,000 sailors died. And it's partly because they didn't realize they were that close to the shore, to those islands, because they didn't know their longitude very well. So the English government set up an award for an accurate, practical means of determining longitude for vessels, and one of those approaches, there are some astronomical techniques, but the technique we'll be talking about is like just having an accurate timekeeping device.
Okay.
So the clock that won this, that Addie and I saw at Greenwich Observatory, was
It was
invented
several
by
years ago,
John
right?
Harrison,
Okay.
and
Was he a beetle?
No, he was
Okay.
not. He was the fifth beetle.
Okay.
Yeah. So it essentially solved that with this clock. It looks like a giant pocket watch. So it's not one of those super big, cool-looking ones that was the most
Giant
accurate.
pocket watch sounds pretty cool.
It was kind of cool. It's about 5 inches in diameter.
Oh, that's smaller than I expected.
And awkward pause. I hope you didn't hear that. So this watch, they did a test voyage, which was 81 days from Portsmouth to Kingston, Jamaica.
Oh.
They did a calibration on the watch.
You just
and
wanted a Jamaican vacation.
the watch had a calibrated loss rate of about 3 seconds per day. So they took that into account. They said, okay, we're going to assume it's running 3 seconds short each day.
Okay.
And then they did 81 and a quarter days roughly to Jamaica. And then when they got there, they took into account the 3 seconds lost per day. And they said, okay, based on the clock, we think we're at this longitude, but we're actually at Jamaica. That corresponds to a time interval.
Okay.
And the question is, what was the error in the time of that clock after the 81 days, after accounting for its known calibrated error? I'll give you multiple choice.
Okay.
Okay.
And it was all my choices are slow because I couldn't figure it. It was slow, and I didn't see any particular reason trying to mix up fast or slow. So how many seconds slow was it after
Okay.
81 days? 5 seconds, 18 seconds, 29 seconds, 46 seconds, or 59 seconds slow?
And this is accounting for the 3 seconds there.
After you've removed the
that.
3 seconds
Okay.
per day, which works out to whatever, 240, a few minutes, 3.5, 4 minutes.
Okay.
So after accounting for that, it was an additional amount
Okay, that
wrong,
helps.
and that's the part that matters because you do your calibration before you sail.
Sure.
Then when you're navigating, you figure out where you are, and they were 5 seconds off. And then the follow-up question to that will be after I tell you
Could
what
you
the
just give
right
us the
answer
answer?
Did you just give
is.
us the right answer?
Did I?
I don't know.
He said there were 5 seconds off.
Yeah.
A! 5 seconds! Yes!
I think it's A.
Nailed it!
We can pretend like that didn't happen.
Editing.
So mad at myself.
It's a good thing Diego's here today. We can edit that out.
No.
And
Don't look at-
answer.
'cause the
I'm not
second
looking at
part-
anything. I
second
can't
part
see
is here.
anything.
Well, so it's 5 seconds.
We both got it right.
Nice.
Fortunately, I have a follow-up question.
Oh, thank God.
Okay.
And the follow-up question is, what is the corresponding error in longitude, in distance,
Oh, okay.
to that error in time?
Okay.
In other words, the clock is off by 5 seconds. Damn me, Josh. What does that mean if you're the navigator on the ship and you look at the watch and you think that's the right time? How far off is your reckoning of where you are east and west
Sure.
in miles?
Okay. Oh, in
Okay.
Or
miles.
kilometers.
Oh,
if you
4
want.
kilometers. Okay.
Yeah.
Cool.
Okay.
We'll
You're
think about
welcome.
that. We'll think about that.
Yeah. Okay. Let's.
That's really good. Okay.
Yeah. They have the 5 seconds. in
Yeah.
them? I know.
I'm impressed.
Ah.
I totally would have guessed
It was
that.
so good. That's why I blurted it out.
Yeah.
Jumping. Well, let's do a quick Earth topic since we're here
Sure.
on the Earth and talking about this stuff
Mhm.
before we
We sort of
do an
mentioned it already.
explosive leap out
Yeah.
into the cosmos with volcanoes.
Woo!
So
That was what I picked.
Yeah.
yes, we've talked. Of course, everybody's familiar with the KT boundary and the Cambrian mass extinction 65 million years ago, with the death of dinosaurs and more than 90% of species due to an asteroid impact off the Yucatan Peninsula. There have been various other mass extinction events in the history of the Earth, which is kind
Yes.
of terrifying.
Yeah.
Yeah.
Turns out.
There was one at the end of the Permian era, which was the most severe since life sort of took off
Yeah.
on the planet, which has only been the last half a billion years or so, since
not
the
too
so-called Cambrian explosion. And so this event was 252 million years ago, wiped out more than 90% of marine species and more than 75% of terrestrial species.
That's not good.
And
That's not good.
The Siberian Traps Large Igneous Province, also known as St. Lip, or probably not really, but STLIP, is a large continental flood basalt province, so basalt being
Volcano material.
Yeah,
Okay.
and so it's presumed that that was a trigger event for
Okay.
this due to dating. And so they have basically confirmed that the initial eruption of that thing started about 300,000 years before the extinction, at least in the oceans. But what I found unsettling about this is, for some reason, like I asked you guys, volcano or earthquake,
Mm-hmm.
if I had said volcano or impactor, and which is more scary, I would have said volcano is more scary.
Because it's more likely?
Yeah.
Yeah.
I just sort of feel like, the Earth could just...
The Yellowstone supervolcano?
Yeah.
Oh, terrifying.
And basically what happens, with it, whether it's an impactor or a volcano, you basically get massive climate change.
Yeah.
And
turns out we don't need an impactor or a volcano.
Turns out we're the impactor.
Unfortunately, there are other ways you can get climate change as well, and what's terrifying is that the climate change that was produced by these volcanic events killed 90% of all the species in the ocean and 75% of all the species on land.
And in this case, it wasn't just, so a lot of times when we think about the climate change, is because you think about, well, the volcanic activity puts all of this stuff up into the atmosphere, and typically that seeds clouds, and you have a lot more cloud cover for longer, so it's cold.
Right.
And similar thing happened probably with the dinosaur impact. The dinosaur killing impact was that it just got cold for a while.
And dark, and plants die, and there's nothing to eat.
There's nothing to eat. Dinosaurs get cold, they get chilly.
Yeah. So this particular study looked at the abundance of nickel in the layers corresponding to that time period, and showed that the changes in chemistry in the ocean would have resulted in a lot more production of methane from little microorganisms that are methanogenic. And
so it's good for them.
The chemistry of the ocean.
It was good for the methanogenic organisms, and it was very bad for things that like oxygen.
Right.
No, we like oxygen.
We like oxygen. Yeah. So that's, I think, an interesting connection between sort of geophysics and biology and astronomy and all these different things you can have similar effects from a number of different sources.
Yeah.
Right.
I also thought it was interesting that most microorganisms, a lot of them need nickel as like a trace element in their diet. It's kind of like we need a little bit of iodine in our diet, right? But you don't want lots and lots and lots of it because it messes up your chemistry.
Right. Yeah. So there you have it. Sometimes it's asteroids, sometimes it's volcanoes.
Sometimes it's
Sometimes it's tailpipes.
Yeah. Yeah. I think the thing about this climate change stuff that a lot of people don't realize is the rate. I mean, it's all about the rate of these changes, right? I mean, obviously the climate slowly changes over time, all the time, right? Because of astronomical forcing things. If things change slowly enough, it's okay. Things adapt and whatever.
You have time to adapt.
Right. It's when you get very quick climate changes. And that's exactly what's happening now.
And it seems like it's kind of slow because you're like, oh, it's going to be 30 years.
Because over the course of
fast.
human lifetime, but geologically speaking, it is changing ridiculously rapidly, and of course, it's leading to extinctions, and will lead to lots of extinctions for the next foreseeable future.
Yeah, and it is changing quite rapidly and accelerating, and Well, and one of
She's putting on a happy face.
You're just being an optimist.
Yeah.
I mean, one of the things that we learned from history of these things is that if, for example, a giant volcanic eruption did not result in climate change producing mass extinctions, then you could sort of relax about your anthropogenic CO2, because you could say, look, the Earth system is a well-buffered
Right.
system. The
Yes.
climate system is well buffered, and it can handle, a big perturbation.
We do not
the
have a buffer.
history
Our internet
of-
is down.
Yeah, the history of the Earth is when there are perturbations, it slams over from one state to another state. It is not a super stable system. The climate is very unstable. It goes from very hot to very cold on relatively short time scales with relatively small perturbations.
Yep.
Yep.
So that's volcanoes, a big volcano, smaller than the planet,
But it has planetary consequences.
Yeah. So it's that history of all these natural changes that resulted in very rapid and very catastrophic sort of state changes of the climate that are, as I said earlier,
But
terrifying.
hey, we could always hope for an impactor.
More terrifying than black holes.
Yeah, they're far away. I'm not too worried about
Yeah.
that.
Our colleague Brendan Byrne at NPR is more worried about black holes, but I'm more worried about volcanoes.
Yeah, that's
And
impactors.
CO2.
What about the very dangerous supernovae?
I'm less
they're
worried
also
about
not
those.
super close.
I'm less worried about those, but we do have supernova news.
Yeah, some fun supernova news that is, in some
Good.
sense.
I didn't want boring supernova news.
Yeah. Well, it's hard to find boring supernova
I
news.
know.
In some sense, a third kind of supernova has been finally detected.
What are the first two kinds?
So, supernova is just a great big giant explosion, of course.
Sure.
The first two kinds are the massive star supernova, which is where a really big star converts all of its core into iron at the end of its life, and then that
Nice.
iron kind of catastrophically collapses and causes the star to rebound out and release a huge amount of energy in a very short period of time.
Just like that.
Good demonstration.
The other kind of supernova is very different. There's a white dwarf supernova, right, where a white dwarf sucks material from its companion star and gets too heavy, and then suddenly turns into a big giant thermonuclear bomb.
A white dwarf is mostly carbon, right?
Right, white dwarf is a
Yes.
big giant ball of mostly carbon, but it's
densely packed.
very
but
extremely
it's still
dense.
carbon.
Right, it's a bunch of carbon, but it.
Just like you.
But there's some like maximum mass to a this big giant ball of carbon, because it's being held up by this fancy thing called the electron degeneracy pressure. And if you add too much mass onto there, that fails catastrophically and quickly. And then you take this whole thing that is a big pile of carbon
House
and
of
do a whole bunch
Cards.
of nuclear reactions all of a sudden, and that blows the whole star apart.
Yay.
And the thing is
And we
that
can tell the difference between those. I mean, they look different.
They look different.
they look a little bit different. I mean, at first glance, very similar, which is why they both have the name supernova, even though
they're
they're totally different phenomena.
Processes, right.
They're big explodey things.
But they're
in the
big
sky.
explodey things in space. But
And they're
if you look
super
at them
bright.
carefully, they look quite different. That is how bright they get, how quickly they get bright, and how quickly they get dim, and the specific wavelengths of light
Right.
are all subtly different. And so you can tell the difference between the two. For at least the last couple decades, we've been positing the existence of a third kind, kind of an in-between kind. So there are some stars that aren't quite massive enough to take their cores and make them all iron.
Okay.
They end up with cores that are largely neon and magnesium and oxygen. And so these are stars in a fairly narrow range of masses, maybe 8 to 10 solar mass to begin with
Correct
stars.
me if I'm wrong, Jim, but isn't neon the fifth most abundant element in the universe?
It could be. I've forgotten already, even though I gave that.
You gave it. You didn't get to retain it.
But these things can undergo, it turns out, supernova as well. At least we think it's really reasonably well modeled. If, and this is called an electron capture supernova, which actually, in some sense, that iron collapsing one is also an electron capture one. You get this situation where if they get heavy enough, the electrons and the protons in those neons and magnesiums combine. And what happens if you take a proton and an electron and smash them together?
You get a neutron.
You get a neutron. And that changes, right? Basically, in this case, the problem is now all the electrons are gone. But the electrons were the thing which were providing the pressure
Right.
to
Holding it
hold
up.
the thing up from collapse.
Right.
And
Because so yeah, I mean, lots of electrons, bunch of negative charges. They're on the outside of the atom, so they push each other apart, and that's kind of what's holding up the white dwarf and that electron degeneracy pressure you mentioned, and it's what keeps us from falling through the
That's why you can never actually touch the table.
Well, we should be
the
careful.
same.
This is a very
It's not
different,
the same.
actually, phenomenon. But
Okay.
we don't fall through the table just because of standard electromagnetic forces. Electrons pushing on other electrons.
Okay,
And
is this different?
this is different.
Yeah.
This is trying to pile too many electrons into exactly the same place. And
That's the electron degeneracy
Right.
pressure.
Yeah.
Right.
Okay.
Right, but
So-
if I all of a sudden have no more electrons or many fewer electrons, then that source of pressure is gone. And if I still have the crushing gravity, and all of a sudden I remove the source of pressure, then the whole thing, bam, collapses and explodes.
So the question, and I think we've talked about this before, is an atom is a positive nucleus surrounded by a bunch of negative electrons. How come this isn't happening all the time? How come we're not just all a bunch of electron capture supernova as soon as you wake up in the morning?
Right.
I feel like that sometimes.
How come all those electrons aren't just slamming down
like-
into their nuclei?
Right, because they
have too much energy.
They have too much energy, right? It's just like why the Earth isn't falling into
To
the
the
sun
sun.
constantly.
So what is it that makes that, what is the thing that overcomes that energy that causes that electron capture? Is that the essential element? Or
Well,
aspect of
so
this
it's just like if the gravity is high enough, if you're piling those electrons in, so many of those electrons into so many of those atoms, they're getting closer and closer and closer and closer, and eventually there's just nowhere else for those electrons to go except
That
smack
space.
into nuclei,
Okay.
and then
It's like you can
get
even
captured.
magnets that repel each other sometimes if you're strong enough.
That's right. That's right.
Not
And
really
that's what happens.
getting
It's
magnets.
gravity that's providing that extra beefy strength that you need, and because as these the nuclei of these stars, as time goes on, there's more and more stuff kind of raining onto them, right, from the puffy outer layers of the star that are still doing some fusion. So they're fusing things. Stuff is raining down onto the core of the star, which is fairly inert, but it's getting more and more massive, and more massive means more gravity, more gravity, more gravity, and everything gets smushed in there, and then bam, electron capture begins, and then this starts off a, most of the times in astronomy, the
Cascade.
processes we talk about take
True.
millions, billions. This takes seconds once it starts, right, and the whole thing blows up,
In less time than climate change.
right.
Yeah.
And the nice thing is, this kind of electron capture supernova, which is going to be really rare compared to the other kinds, but it has a very specific kind of ramping
Signature.
up and signature.
So
it's
that's
been
the
predicted
signature
for
they think they've seen.
It's
And
been
this is-
predicted
right.
for a while, but we've finally seen one.
We've finally seen one, kind of definitively seen one, and so that's great because that's more. Our theories are good.
Are working.
Yeah,
Hooray.
it's pretty cool.
Okay.
Good job, theories.
Well
Yeah.
done. Let's see if you can get this one though, smarty
Okay.
pants. How many seconds off was that clock? I'm not even going to give you choices.
I'm going to say like 5
What? You need units on that.
seconds. You said how many seconds off was the clock?
I did.
Oh, yeah, I'll go with C.
Uh,
5?
Addie takes this one.
Oh, man.
It was actually A, 5 seconds slow. Well done, Addie.
Man.
Yes.
What
So
is the
dumb.
corresponding error in longitude to this time error? So you're on the ship, you look at the clock, it says it's 12 o'clock. It's really 12 o'clock and 5 seconds. But based on your calculation thing, it's 12 o'clock. Where do you think you are? How far east or west of your actual location do you think you are?
So 4 minutes is 1 degree.
Oh, I did all the same thing. I was trying to figure this out.
Yeah, 4 minutes is 1 degree.
And I
Then
had the benefit of having the right answer in front of me.
5 seconds is 1/10 of a minute, and so roughly.
Okay.
Spit it out. You got to go for it.
I'm not fast enough with the calculations in my head.
You had all this time to be thinking about it since you knew what the
degrees.
right
Oh,
answer
but then you have to.
About supernova.
20
Then I have
minutes
to go
ago.
from degrees to meters and stuff. Oh gosh, so 10 kilometers.
10 kilometers, Jim says.
I'm gonna say 5 kilometers.
Yeah, I want to say less now. 500 meters.
Oh, okay.
Well, are you going to modify your
No.
answer? I don't know.
I'm fine with it, I'm fine
Well,
with
the
it.
answer is about 2,000 meters, if we want to do it in meters, about 1.2 miles.
What is it? Oh, it's achievements.
So about 2 kilometers.
Okay.
500 meters is technically closer to that.
Yeah,
in
but
an
she's-
arithmetic sense, but not
right,
in a
logarithmically
logarithmic
she
sense. Yeah.
I'll give it to
So
her.
it was only off by 1 1/4 miles, which is pretty good. the Longitude Act, which was supposed to reward whoever came up in England, whoever came up with a good system for determining longitude, the reward amounts were 10,000 pounds sterling for an accuracy of 1 degree in longitude at the equator. Kingston, Jamaica is about 18 degrees latitude, is pretty close to the equator. So his error with this clock was about 1/50th of a degree.
Yeah.
So the reward was 10,000 pounds for 1 degree, 15,000 pounds for 2/3 of a degree or 40 minutes of arc, 20,000 pounds the full prize for half a degree or 30 minutes of arc. His clock was 1 minute of arc, 1.25 minutes of arc. So he blew it away.
Nice.
Yeah, but he
Guess
still
what?
just got the 30.
They didn't give him anything.
What?
He came back and they're like, well, we think you just got lucky. Do it again.
Did he do it again?
He did do it again.
And
And it wasn't quite as good that time, but it was still way below
Yeah.
the 30 arc minute thing. And they're like, well, we'll give you 5,000 pounds.
What?
What?
If they said they're going to give him 20,000 pounds?
Because we think that their errors just fortuitously canceled out. Or
What?
something like that.
Oh, this is not.
So he had, basically his whole life was spent arguing with Parliament about getting money for these things. Because he built a clock and they're like, oh, this looks promising, here's 500 pounds. Then he does some stuff, he builds stuff. Then they're like, well, your clock is too complicated and to win the prize it has to be practical.
It was a pocket watch.
Yeah, but it took him years to build, of course, as a prototype.
Yeah,
right?
sure.
Then he goes to the king.
He needed a Kickstarter.
And the king was on his side, and the king's like, damn it, you get, then he went back to Parliament, and they're like, well, we'll give you 8,000 and some pounds. Over the course of his life, he did get about 20,000 pounds for all the variety of clocks and things like that he did, but the last big chunk, the significant thing, was still much less than he was supposed to get, was when he was like 79 years old.
Yeah, too old to spend it.
Yeah, yeah. So it was an very interesting story, and those clocks, the earlier clocks, were big, complicated. And one reason it's complicated is at that time, a lot of clocks were based on balances. And if you're on a ship that's tossing and turning, that totally screws those things up.
Yeah.
Right.
So that was that was a reason it was a very complicated endeavor to go through.
Yeah.
Anyway, well done. I can't believe you got the 5 seconds.
I know.
That's pretty amazing.
Nice job, Addie.
Thanks.
Yeah. Well, while it may have felt like your atomic clock needs a reset, it was just another episode of Walkabout the Galaxy. Help us grow our listenership numbers by a factor of 10 by getting 10 new phones, tablets, or computers, creating new email identities for each one, and subscribing to us on each of those 10 new devices. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, where you can see most of our episodes, some of our bloopers, and all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jerusik. Diego Rodriguez is our production video assistant. Thanks to our listeners in Berlin, Potsdam, and surrounding areas, and around the planet.
Wow.
Be excellent to each other.
Yes.
It's a new tagline.
New thing you're saying?
Yeah.
All right.
I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the Astroquarks, signing off until the next episode of Walkabout the Galaxy. 5 seconds. Double DSAC.